From steel plate to underground pipeline, witness the fascinating journey of pipe manufacturing and installation. Founded in 1973, Ventec pioneered the first induction bending machine in North America and has since become the most experienced induction vendor with over 95,000 bends in service today. Strategically located in Duluth, Minnesota, near the inland freshwater port, Ventec benefits from excellent logistical access for worldwide shipping by sea, truck, or rail. The company serves a wide range of industries, including pipeline construction, power generation, and architecture, offering everything from traditional bends to large radius custom shapes. Ventec is an ASME-certified facility holding the SU and PP stamps, ensuring strict compliance with international standards. All incoming materials are carefully inspected, PMI tested, and verified against mill test reports before being assigned a unique identification number for full traceability. The company's on-site laboratory performs tensile, hardness, metallurgical, and CBN tests, guaranteeing that only the highest quality materials are used in production. Equipped with two custom-designed induction bending machines, Ventec can handle pipe sizes from 2.5 inches to 66 inches in diameter, and wall thicknesses up to 6 inches. They can bend carbon, stainless, and chrome alloy steels meeting ASME, API, and ASTM specifications. The process begins with shot blasting to remove surface contaminants, followed by precision-controlled induction heating and bending. Bends can be made with radii as tight as 1.5D or to any custom specification. Additional post-bending treatments include stress relief, normalization, and quench and temper heat treatment, ensuring excellent mechanical and metallurgical properties. Every bend undergoes non-destructive testing such as ultrasonic, radiographic, and magnetic particle inspections to ensure integrity and compliance. For corrosion protection, Ventec applies liquid or fusion-bonded epoxy coatings, along with paint for above-ground applications. Before shipment, all bends are dimensionally verified, machined, coated, and inspected under NACE-certified supervision. Each finished product is carefully packaged and accompanied by a complete data dossier documenting all production and inspection stages. Through advanced technology, rigorous quality control, and decades of expertise, Ventec has earned a solid reputation for reliability, precision, and innovation in the pipe bending industry, delivering turnkey solutions from raw material to finished bend. The manufacturing process of longitudinal submerged arc welded steel pipes begins with the use of a magnet lifter to lift and transport large steel plates to the production line. These plates are then fed into an edge milling machine, which accurately trims and bevels both edges of the plate to achieve the proper welding angle and ensure a precise fit during forming. Next, the plate passes through the pre-bender machine, where the edges are slightly bent to prepare for the forming stage. The in-feeder machine then positions and aligns the plate correctly before it enters the JCO press bending machine. In this machine, the plate is gradually shaped into a J, then a C, and finally an O configuration, forming a cylindrical pipe. The semi-formed pipe is transferred using a turning transfer car to the tack welding machine, where the edges are temporarily joined by a small weld to maintain shape and alignment. The pipe then undergoes inside welding, where a submerged arc welding head travels along the inner seam, fusing the edges together with high precision. Following that, the back bead cutting machine removes excess weld metal from the inner surface to create a smooth interior finish. Subsequently, the pipe is turned over and sent to the outside welding machine, which performs a submerged arc weld along the external seam to complete the longitudinal weld. The four-way machine, also called the impending machine, checks the pipe's shape and roundness, making corrections if necessary. After welding, the pipe ends are machined by the end-facing machine to achieve smooth, perpendicular edges suitable for joining. The pipe is then cleaned in the washing device to remove oil, scale, and debris from the surface. For quality assurance, each pipe undergoes non-destructive testing using the X-ray test machine, which scans the weld seam to detect any internal defects. The inspected pipe is transferred by a turning conveyor to the coating section. Finally, the varnish coating machine applies a protective layer on the outer surface to prevent corrosion and ensure a clean, finished appearance. Through these sequential steps, the LSAW process ensures the production of high-quality, dimensionally accurate, and structurally sound steel pipes suitable for use in pipelines, construction, and other industrial applications. Bentech is a world-class steel fabrication company with over 100 years of excellence, recognized globally for its expertise, dependability, and innovation. The company provides complete steel fabrication services in accordance with all ASME B31 piping codes and AISC structural standards. With a 160,000 square foot facility, 5 acres of storage, and 60-ton indoor crane capacity, Bentech can handle any project, large or small, and Bentech introduced induction bending to North America in the early 1970s and remains the most experienced facility in the country with over 95,000 bends in service. Its custom machines can bend all ASTM and ASME grade materials, ensuring reduced field welds, improved inspection quality, and precise stress control. The company's quality assurance program meets ASME boiler and pressure vessel code standards and includes advanced non-destructive testing, grit blasting, and painting facilities. Through skilled certified welders, strict process control, and continuous innovation, Bentech guarantees the highest level of quality, safety, and customer satisfaction in every fabrication project. The pipe manufacturing process begins with the storage of steel plates in the yard. Each plate is identified and numbered for traceability. Before any forming takes place, the plates undergo an edge milling operation. This step is essential to prepare the plate edges for welding. Using an edge milling machine, both sides of the plate are precisely milled to achieve smooth, clean edges with the proper bevel angle. Accurate edge preparation helps ensure the correct fit-up and high-quality welds during subsequent stages. After milling, the plates are transferred to the 3-roll bending machine, where they are gradually shaped into a cylindrical form. The rolling process begins with the plate positioned between the 3 rollers. As the rollers rotate, the plate is bent step by step until the two edges come close together, forming a pipe shell. Proper alignment during rolling is critical to maintaining a uniform diameter and preventing any deformation. Next comes post-bending, a fine-tuning step to correct roundness and ensure the seam edges are properly aligned. The operators check the geometry of the bent plate to verify that it meets the design specifications before welding. Once the shape is satisfactory, the pipe shell proceeds to the tack welding machine. Tack welding temporarily joins the edges of the plate with short welds to hold the pipe's form and alignment before the full welding operation. These tack welds are carefully inspected to confirm the seam is uniform and straight. Following this, the pipe enters the pipe pressing section, where it is prepared for internal welding. This step ensures the seam is tightly closed and properly aligned for the main welding process. The internal welding stage begins with a submerged arc welding machine that moves along the inner seam of the pipe. The internal weld provides structural strength and seals the joint from the inside. After completing the internal weld, the pipe is rotated to the external welding station. Here, another SAW machine performs the external weld along the outer seam. The combination of internal and external welding guarantees the full penetration and durability of the joint, creating a strong, high-quality longitudinal seam pipe. After welding, the pipe moves into the inspection and testing stages to ensure it meets the required standards. The process begins with pre-washing, carried out by a pre-washing machine. This step removes any welding slag, dust, or grease that might interfere with subsequent inspections. Clean surfaces are essential for accurate testing and coating adhesion. Next, the pipe enters the expander. In this step, mechanical or hydraulic expansion is applied to bring the pipe to its final diameter and roundness. The expansion process also helps release residual stresses induced during welding and forming, improving the dimensional accuracy and structural integrity of the pipe. After expansion, the pipe passes through the post-washing machine, where it is thoroughly cleaned again to remove any residues or contaminants left from the expansion process. The next crucial stage is the hydrostatic test, performed on the pipe hydrotest machine. Each pipe is filled with water and pressurized to a specified test pressure to check for leaks or weaknesses in the weld seam and body. The pipe must maintain pressure for a certain period without any loss to pass this test. Following hydrotesting, non-destructive testing begins. The ultrasonic testing machine is used for welding detection, scanning the weld seam for internal flaws, such as cracks, inclusions, or lack of fusion. Then, the pipe is inspected by an X-ray real-time machine, which provides continuous imaging of the weld to identify any internal defects not visible to ultrasonic testing. Once the weld integrity is confirmed, the pipe undergoes end beveling on the beveling machine. This operation shapes the pipe ends to the required bevel angle, ensuring proper joint preparation for field welding or assembly. Finally, every pipe is subjected to a final visual inspection. Skilled inspectors examine the entire pipe surface, weld seams, and dimensions to ensure compliance with specifications and quality standards. Only pipes that pass all inspections are approved for coating, marking, and dispatch to customers. At Immingham, the unloading of over 600 pipes begins from the vessel, consisting mainly of 14-meter lengths with some shorter sections made for the project. The pipes are packed tightly to prevent movement during transport. Workers lift 3 pipes at a time directly into waiting trucks using excavators equipped with vacuum lifters, ensuring stability and control. Once unloaded, the pipes are stacked in the storage yard, where 10% are selected for detailed inspection. Each inspected pipe undergoes visual checks, thickness testing of both polyethylene coating and internal epoxy lining, and salt contamination testing. Any detected damage is repaired on-site using Canusa products. After inspection and repair, the pipes are recapped, reloaded onto trucks, and transported daily to the project site for installation. The pipeline installation process for the OCV-API and OCV-AP2 projects began with the preparation and assembly of the permanent ventilation system inside the tunnel. The first step was the installation of 2 powerful fans, one axial and one centrifugal, designed to ensure continuous ventilation throughout the construction phase. These units maintain the necessary air circulation, removing dust, smoke, and welding gases. After the fans were positioned and secured, approximately 400 meters of flexible ducts were assembled and suspended along the tunnel walls to distribute fresh air evenly. The ducts were connected in segments, forming a continuous ventilation line from the tunnel entrance to the farthest working zones. At the same time, drilling operations were carried out on the curved concrete staves of the tunnel lining to prepare openings and anchor points for future support brackets and structures. Once the ventilation and preliminary drilling tasks were completed, the process moved to the production of pipeline support brackets, which were essential for holding and stabilizing the pipelines during and after launching. The fabrication started with laser cutting of steel plates, using precise numerical control to obtain perfectly shaped components according to design drawings. The laser-cut pieces were then cleaned, aligned, and assembled by skilled technicians. Each bracket was welded along its joints and edges to provide structural integrity. After welding, finishing operations such as grinding and polishing were performed to remove irregularities and ensure accurate dimensions. The finished brackets were then sent to the surface treatment area, where they received a metallic coating to protect against corrosion, followed by painting with high-resistance industrial coatings. Simultaneously, concrete bases were constructed and cast in predetermined positions to serve as the foundations for the permanent supports inside the tunnel. Following fabrication, the assembly team began the installation of the permanent structural supports. The process included the positioning and fixation of 30 brackets in the NATM section, providing the initial support for the 2 main pipelines to be launched. Each bracket was aligned using laser-level instruments to maintain perfect geometry. In the TBM section, additional operations were executed to transport and install the remaining support brackets. A total of 492 brackets were placed along the tunnel to ensure continuous and stable support. Specialized lifting and anchoring tools were used to position each bracket safely within the confined underground environment. Parallel to this activity, the production and installation of drive rollers supplied by Litoral were initiated. These rollers played a vital role in enabling the controlled launching and movement of the pipeline segments through the tunnel. Before installation, drilling jigs were employed to create accurate mounting points on the curved concrete staves. The drive rollers were then positioned, anchored, and tested for proper rotation and alignment. Once the roller system was fully assembled, it was capable of supporting and propelling the heavy steel pipes with precision during the launching phase. Subsequently, the construction and assembly of the launching structure for the pipelines took place. This structure extended approximately 100 meters into the tunnel and was fully equipped with Litoral drive rollers. It functioned as the main platform for continuous pipe launching. A command and control cabin was installed beside the structure to monitor roller operation, adjust alignment, and coordinate pipe movement. Simultaneously, the construction team executed the setting of root piles, forming the deep foundations necessary for supporting the entire launching system and associated pipe racks. Once the piles reached the designed depth, they were concreted and tested for load-bearing capacity. The next major task was the construction of pipe rack supports at the tunnel entrance. These racks held the pipe segments before insertion into the tunnel. Each pipe, formed from double-jointed sections, was carefully loaded onto the Litoral drive rollers. The launching operation followed a systematic sequence, coupling two pipes, welding the joint, performing visual and radiographic inspection, and applying an external protective coating. This routine ensured that every connection met stringent mechanical and quality standards. After verification, the pipes were progressively launched into the tunnel using the roller system, advancing smoothly along the prepared supports. The launching of the pipelines was executed continuously, with real-time monitoring of alignment and elevation. Adjustment devices were used to correct any deviation as the pipes advanced deeper into the tunnel. Once the first pipeline was fully inserted and positioned, the team began launching the second one in parallel. The entire operation demanded precise coordination among welding, inspection, and control teams to maintain safety and efficiency. After completion of the launching phase, attention shifted to the construction and assembly of the external pipe rack that connected the above-ground facilities with the tunnel section. This structure supported the transition of the pipelines between the open area and the underground alignment. Inside the tunnel, final installation steps included welding of circumferential joints, non-destructive inspection, hydraulic testing, and coating of weld seams to restore anti-corrosion protection. The entire underground portion, measuring about 5 kilometers, was thoroughly inspected to confirm structural integrity and tightness. One of the significant challenges of this operation was the launching of the new pipeline directly above the existing GASTAU 28-inch pipeline, which remained in service. To avoid interference, the new line was positioned with minimal clearance and supported by specially designed brackets. Once the first pipeline was secured, the second pipeline was launched parallel to it, following the same coupling, welding, inspection, and coating procedures. Both pipelines were finally aligned and fixed along their entire lengths before connection with the shaft area at the far end of the tunnel. When the mechanical installation was completed, the project entered the commissioning stage. The primary activity in this phase was PIG handling. Special pipeline inspection gauges, known as PIGs, were inserted into the pipelines to clean internal surfaces and verify the continuity of the line. These PIGs traveled through the entire 5-kilometer section, collecting data and removing debris, weld slag, and coating residues. After PIG, pressure testing was performed to confirm leak tightness and mechanical strength under operating conditions. The lifting operation begins by securing the pipe firmly with heavy-duty slings and wire ropes. Riggers carefully position the lifting belts around the pipe to ensure proper balance and stability during hoisting. Once the pipe is tightly fixed, the crawler crane operator slowly increases the tension on the ropes to check the alignment and load distribution. After confirming everything is secure, the crane begins lifting the pipe steadily off the ground. Riggers on the ground guide the movement using hand signals, maintaining constant communication with the crane operator. The pipe is then lifted to the required height and carefully moved to its designated position. Finally, it is gently lowered and precisely placed onto the supports, where the riggers release the slings and verify that the pipe is stable and correctly aligned before the next operation begins. The automatic pipe welding machine is designed for efficient, precise, and consistent welding of pipes. It uses advanced sensors and programmable controls to ensure uniform weld quality with minimal human intervention. The machine can handle various pipe diameters and materials, offering high productivity and excellent repeatability. Its automated system reduces labor costs, improves safety, and ensures strong, reliable joints suitable for industrial applications. The GridGuard pipeline protection test demonstrates the product's ability to shield pipelines from impact damage during backfilling. In the test, a section of GridGuard rock shield is placed over a protected pipe to simulate real installation conditions. Then, 3-inch gravel is dropped from a height of 10 feet directly onto the covered pipe. This procedure replicates the harsh conditions that may occur when heavy rocks or gravel fall during trench backfill operations. Throughout the test, the GridGuard layer effectively absorbs and disperses the impact energy, preventing direct contact and deformation of the pipeline's surface. After the drop, inspection shows that the pipe remains intact and free of dents or coating damage. The rock shield maintains its structural integrity, confirming its excellent resistance to puncture and compression. This test verifies GridGuard's superior protective performance, ensuring the long-term safety and reliability of pipelines even in demanding construction environments. Several 12-inch pipes are bent using the DMI open-face 6-20 bending machine. equipped with a 12-inch pneumatic clamp from SCAIP. First, the pipe is carefully positioned on the bending die and secured by the pneumatic clamp to prevent movement during the process. The hydraulic cylinders of the DMI machine then apply controlled pressure, gradually forcing the pipe to bend around the die to the required angle. The open-face design allows easy alignment and precise control of curvature, ensuring smooth and uniform bends without deformation or wrinkles. After reaching the desired bend angle, the pressure is released and the pipe is removed for inspection. Each bend is verified for accuracy and conformity to specifications before being placed on supports for the next operation. This process ensures high precision and consistency in pipeline construction